Thank you very much, Pele, and for the invitation and offering this opportunity for me to come here to share with the excellent people. I was really impressed by the atmosphere and the environment of digital futures. I should be here early. So as Khaled said, I have been working on this many different aspects of the automation systems, and hope to use this opportunity to share with you my personal reflections and experiences, also some challenges that I look for some collaboration with academic partners. And before I start the presentation, I'd like to emphasize this is just some academic dialogue. It is not representing the ABB, some official statement in these areas. Don't overinterpret the messages from this presentation. So see this as my like just interactions with academic people and inspire future research together. And the topic is control over the cloud and fog for automation, for advanced digitalization or industries. It's a bit fancy. Before I start the presentation, I'd like to introduce the company first. Maybe for some of you, ABB is not a very well-known name because we don't do the consumer business. We only deliver our products, services to the companies. So ABB, we say, is electrification and automation company. We have the four main business areas. First is electrification. It's a low and medium voltage power electronics, power supply for factories, for buildings, for the city infrastructure. For example, the EV charging system. And we have the second one is process automation. It includes the hardware, the sensors, actuators, controllers, and the control system, the DCS, for all the type of the process industry factories. And then we have the robotics, motion, that is the motors, or different size of motors, can be very small, can be super big motors, and also the drive system behind the motor. And then the last one is the robotics and the machine automation. We produce the robots. Maybe this is the most well-known product from ABB because it is shown everywhere. It is used in the automotive industry, basically, and also expanding to the service scenarios, like the hospitals. Even in the future, in the restaurants, you will see more and more robotics. In these business areas, ABB is ranked number 1 or number 2 in general. Basically, we are leading player in the automation world. We are providing almost everything about automation, we could say. And this is the agenda of this presentation today. First, I share with you the vision about cloud fog automation. It's still a very fancy concept. It is more about using the cloud and the fog computing for deploying the future new generation of the automation systems. And then look at where we are today, especially about the 5G technology and for this vision. And then how much can we do from the control side? It's not just the communication and computing challenge. If we do something from the control models, we believe it can make things much easier. And then the future perspectives. So even though we have done something, we believe the challenges are even bigger than what we understood. So we do need this cross-disciplinary research. We need the expertise from all the 3 subjects, communication, computing, and control, to solve the challenges. And I also like to acknowledge the contributions from my colleagues, my students, and collaborators in the recent years in this area. Yeah, first, it's about cloud fog automation. For this picture, maybe the right side is easier to understand. They are the scenarios of this automation systems. It can be in the factory, can be in the infrastructure, can be the energy power plant, can be even in some like offshore platforms for oil gas, and the vessels, the big vessels, the onboard automation systems for the vessels. If you look at the abstract, the technologies behind these automation systems, they always look like this. You have a lot of high-level workstations, software, the DCS, then you have the controllers. They are connected over different type of networks. They are distributed decision-making system. Then for the controllers, it gets the data from the sensors, from the input devices, then make decision, then give back the feedback command, control command to the actuators. Depending on the applications, there are different types of the controllers and sensors, actuators. But in general, the architecture looks like this. It is a layer structure. We call that the pyramid automation structure. On the top level, it is the ERP system, enterprise resource planning. It's the high-level software manage the orders from the buyers and supply chain, and then in the middle it is the manufacturing execution system or some collaborative production management system, depending on that. There can be different names, but the task of this layer is the same. It dispatch the orders into some production plan, then give this plan to the lower level control systems. Then you have the supervisory control. This is a bit higher level of the control task. It will execute the production plan for the MES. Typically, it controls one production line, one process. Then go one level lower, that is regulatory control. This level is much more time critical than the supervisory control. In this level, it manages the very fast control loops. Actually, this loop cycle time can be also very diverse depending on the different applications. It can be from 100 millisecond to 100 microsecond. So this is basically the most challenging level of the control task. It needs real time, it needs very precise, very reliable and deterministic behavior of the communication, computing, and control. Then the bottom is the process. It can be a chemical process, physical process, some hybrid, even some bio process. Notice that pyramid structure is the result from the Industry 3.0, the third revolution of industries. It's automation technology. But what is happening now when we have the fourth revolution of industries? So here I give just a few game changers. I call that game changers because they are really changing the things and also the way that we do all the things. The first is Internet of Things. We know so the communication technologies is expanding from the human communication to these machine type communications. It is connecting almost everything everywhere. You can get the data from almost everything in our life. This is also happening in the industrial world, in the factories. More and more sensors are deployed everywhere. You can get the information from all the machines nearly. So this is about the connectivity. Then second is about computing. And the computation power is growing so quickly. It's driven by the Moore's law and the processors and the storage of the information is developing so fast. And but today, most of the factory control systems are still using the old generation hardware for computing. It is deep embedded devices. Of course, it has a good deterministic performance, hard real time, and also it is certified in many cases for different safety regulations. But how can we utilize this super powerful computing infrastructure? This is a very important topic that we should consider. And then the third one is artificial intelligence. Is that possible to hide that? Okay. It's intelligence. This is another new thing really introduced by this new generation digital technologies. We see that the intelligence can be involved everywhere in the whole life cycle of the automation systems, during the planning phase, design phase, and commissioning and the maintenance, everywhere. And it is really delivering the value of the new generation infrastructure. So you get the data from the IoT, right? You have more powerful computing. So what do you do? What do you deliver to the customers? That is optimization. More, for example, energy efficiency, or higher quality from the product. And thus, this is the value. So the AI, we could say the AI stuff, applications powered by the AI will be the most attractive values that is supposed to be delivered to the customers. And another important thing is, for all the three things, it has gathered or attracted so much investment and also the best talents. I believe they will become self-fulfilling. That means if everyone believes that will happen, it really will happen. So it is just a matter of time, I believe. And then this is the high-level abstraction about the trend towards this cloud and fog computing for automation. We use this fancy term, cloud fog automation. This is the layer structure, the pyramid automation structure. So this is not just the logical structure, but also the physical structure. If you go to the factories, you will see the IOs, controllers, and networks. They are really organized, installed in such a way, layered. And what is happening already now, it is cloud automation. The high-level applications, for example, ERP, MES, and partly the supervisory control are being deployed more and more to some cloud platform or edge computing platform. And of course, the industries are realistic and conservative. They start from this outside, from this less critical applications. If anything goes wrong, if the latency is too long, if even there's some security attacks, it would not damage the whole process. It will not cause the dangerous impact to human life or to environment. So that's why it starts from outside, approaching the critical part. But there is also already some industrial initiatives driving this kind of change. For example, the NAMUR is one. The NAMUR open architecture is really promoting this concept, the NOA. And also the OPC UA Foundation is also promoting to use some unified communication protocols to collect the data everywhere and use that for this high-level monitoring and optimization of the processes. But in this case, anyway, the most critical part here, the regulatory control, the lower level IO operations, decision making, they are still in the traditional hardware and software architecture. This is due to the security and safety concerns. But the new way of the more aggressive vision is cloud fog automation. Here, we do really want to change this also to this more fog-based infrastructure. Here I use the term fog to reflect the difference between the cloud and edge. And because the fog can be more independent to the cloud. You can, in principle, deploy the fog fully in your facility. You can have a very strong security and safety boundary in between. You can deploy the dedicated hardware for this demilitarized zone. That is the boundary between the public domain and this private sensitive domain. You can do more strong protection. And also, when you do some optimization based on the data collected by the IoT, by this cloud platform, you will change something, right? You need to give the feedback to the process. Then you will pass through this very strong security boundary, so that you can give the feedback in some automatic way. So the idea is not to do the human operation to do this optimization. So otherwise, there's you cannot do this fine-grained optimization feedback. And here there are also some industrial initiative driving this change. For example, the OPAF, the Open Process Automation Forum. This is a big consortium with the involvement from the IT world. Nearly all the famous IT companies, computing, communication companies involved, and also the automation companies involved very much. The large players are all there. Of course, this will take a longer time because the challenge is super big, right? Safety, security. When you ask this question, today we don't have a clear answer. So this is also some prioritized research topics in my day-to-day agenda.
So if you have to put some year on the middle, on the cloud edge, and some year on the cloud edge fog, what would it be? When will you see this in production?
You mean here? You mean the boundary?
No. When if you have to say, you know, when we talk 6G, for instance,
yes.
They say 2030. So when we don't see the cloud automation completely in this way you have it here right now. Correct. So would we see that before 2030? And is the cloud fog automation what?
Yeah, this is just a really personal dream. I think this would happen after between 10 and 20 years.
Okay.
And in general, industries are slower than the consumer domains, right? And also they are very diverse. So the best way of penetrating to the industry is to find, for example, a first use case, which where the wireless or the cloud technology, the AI technology will be some enabler. For example, mobile robots, and also the service robots. So this could be some area of these technologies will become like practice earlier than the other domains. Okay. So the industry has a very wide range, many different segments. We have very different pace of adoption of the new technologies. And actually in the robotics area, there's already some open robotics initiative and some fog robotics initiative about this. Yeah, in general, we say maybe 10 or 20 years to see a broad adoption of this kind of architecture. Then more specifically, the objectives. The first one is about the virtualized computing. As I said today, the industrial devices are using the very deep embedded systems. MCUs with some customized software, with very hard real-time operating systems. But actually now the network infrastructure is providing very powerful computing capacities, like the 5G infrastructure, like the wired broadband networks. They all have these computing capabilities, and also remotely in the data center is super powerful. But to really utilize those computing infrastructure, we need virtualization so that the upper layer developers will not care too much about the low layer stuff. It can provide the same interface and also with guaranteed performance. Providing the interface APIs is easier, but guaranteeing the performance, especially the latency, reliability, and security, quality of service, they are more challenging. But this is really, really needed. Without this, you cannot really use those new things in the industrial world. And another one is deterministic and converged networks. Today, there are super strong technology pushing from the telecom industries, like 5G, and also from the Wi-Fi 6 or Wi-Fi 7. And to really use those new generation communication infrastructure, we need to solve the end-to-end determinism. First, you need to find a proper way to integrate the interfaces. Today, if you look at the machines, motors, robot arms, valve, conveyor belts, they are all using some wired interface, typically industrial Ethernet. So they are these kinds of protocols. They're not there, they're not that. So how to integrate? So there are many tricky things to be done. It's not just plug and play. Similarly, from the controller side, if you virtualize the control logic, control engine, and run that in some data center or cloud computing infrastructure, you also need to solve a lot of interoperability issues. Also, these protocols, because the controllers today are using these protocols. And more importantly, also more challenging is the messages need to pass through all those virtualization layers, as I showed just now. So many layers. The messages are transmitted from the physical media, then going up until the application on the top can really use the message. So you need to really solve this virtualization issue and also guarantee the determinism. Sometimes we call this deterministic virtualization. This is a very important topic. Then let's look at where we are today, especially from the 5G perspective. In the recent years, we have worked a lot with our strategic partners on the 5G and also with our engage our customers, because 5G is really promoted everywhere. It promises to give very, very attractive benefits. It is not just replacing the cables by the wireless infrastructure, but also enabling new things. For example, if you have the very high height of the infrastructure, if you have the wide area in rural area, you have this wired infrastructure, wired networks. And if you have mobility, of course, it doesn't make sense to have a cable behind the robot. And if you have a rotating part, typically like the wind turbine with some grinding machines, so cabling is very difficult. And some harsh environment or corrosive environment, the cables can be damaged very easily. And if you don't have access to the land, this is also the case, especially in North America. The land is owned privately. It's very difficult to get the land to even make a cabling under the ground. And in some modern fashion buildings, it is hard to change anything, to add a cable, add a device, or remove a device. The wireless is more natural choice. And also in many industrial facilities, we need the temporary deployment. The devices are just used for a short while. It should be removed immediately after the task is finished. And another special case is that high voltage electricity stuff. In some power systems, in factories, in the energy facilities, there is very big potential between the controller and the control target. You cannot use the metallic cables for communication. Today, the only choice is the optical fiber. But the material of the optic fibers is much shorter than the solid state semiconductors. So this also gives some opportunity for the wireless to contribute there. If we can manage to solve the challenges in the latency reliability, basically the lifetime of these wireless devices is comparable to to the power electronics, solid state devices. Yeah, all these cases give us a stronger motivation to try with the wireless communication. Another aspect, important aspect, is the computing. So 5G is not just communication. This is also computing. It's natively providing this edge computing capacity. And here, the general idea is in the 5G base stations, it can do a lot of computing process. You can offload the computation load and to the base station, and also you can get a very close distance between the producer and the user of the data. And this is really a very natural choice for the high mobility applications to use a 5G as a computing resource. And what is the primary concern today when we talk about this 5G communication and computing for the industry domain, especially for the control applications? I use this dinosaur curve to describe the challenge. It's about determinism, latency, and reliability. So if you describe the performance over latency, you need always give the probability. Otherwise, it is meaningless. So here I use this curve from some old technology developed by IBM many years ago, maybe 15 years ago, the VISA technology. We measure the performance in such a way. First, in the x-axis, that is the latency of the messages delivered from the sender and the receiver. And the y-axis is the probability of this latency distribution. It can be the PDF curve. It can also be some CDF, cumulative distribution function. But anyway, what we want to see is this low probability events. How many packets will experience a longer latency, even though that can be very low probability, but it is really of our concern. For example, in this example, if we set the deadline to be 20 milliseconds here, okay, we can get 10 to the power minus 8 probability. That's pretty good. In some cases, it is really required. In some cases, it can be minus 6. Here, if we just require minus 6, then we can promise 10 milliseconds. This is the meaning of this curve. But actually, most of the consumer-oriented communication or computing technology mainly provide this type of red curve. It has a very big tail. So the effort in the recent years, including the 5G and the 6G in the future, is trying to push this red curve to the left and to the bottom. Well, of course, the cost increase quickly if you want to reduce, especially if you want to cut the tail. That really causes a lot of challenges. You even need to change the design philosophy. For example, introduce the redundancy. That is the most practical way to cut the tail. But the consumer technologies always try to minimize the redundancy. That's the opposite in the design philosophy. And let's look at where we are today. This is some experiment evaluation that we did, almost 1 year ago in our lab together with our 5G partner. Notice that was not using the latest, the best profile of the 5G for the short latency. It was using the EMBB, enhanced mobile broadband. It is more oriented for the consumer application, for the video streaming applications. It's not for the real-time control yet. And but that is the first matured product release of the 5G technology in the market. And we did this long-term evaluation using a real test bed of the automation. We use a controller to produce this cyclic traffic and transmit over the 5G. Then our automation device receives the message and gives the feedback So this is a closed loop control use case. And we also measure this latency of every packet for each direction very precisely for every packet. And also we developed some dedicated hardware software to do this, because to really know, for example, these low probability issues, we need to have a super reliable measurement tools. Otherwise, you cannot say your numbers are trusted or not. Fortunately, we managed to do this, and also I believe this is really a significant progress from the 5G area. If you look at this curve here, this is the this is downstream. This is from the base station to the device. This is upstream. Is from device to the base station direction. For the one direction, if you set deadline to be 50 milliseconds, you could expect to get at least 10 to the power minus 6 reliability. That is very, very impressive. And if we be more conservative, we can reserve some margin for the engineering implementation. We could say this is already capable of doing the control, closing the control loop at some 200 millisecond cycle time. It is not enough to cover all the control use cases, but it can already do a lot. Of course, this is done in our lab. It is nearly the perfect environment for wireless communication. There's no mobility, there's no big obstacles, there's no long distance, but this is already a very good starting point as a reference. Of course, more field test with more harsh environment is necessary to draw the solid conclusion, but this is already a big progress in this area. We are continue working on this computing part. There's no result to share today. Hope next time I can have some results from the computing side. 5G, 5G is also very good computing, a very good server inside. And then, as I said, without changing the control model, we can do the control loop like 200 millisecond cycle time. It is attractive. But let's see how much can we do from the control side to help to make the thing easier. So this is what we call latency-aware control over the cloud and fog. First, we made a real-life testbed, because this control stuff is difficult to really do this by simulation, because the wireless networks is nearly impossible to be precisely modeled by simulation. You can do some high-level simulation of the network behavior, but the physical layer stuff is too complicated. You can never get the precise enough result if you do just the simulation. And then in our case, we have this lab setup of the 5G and Wi-Fi 6, and also a reference network using the industrial Ethernet. And we have this fully virtualized computing environment. It has an industrial PC and servers running some mainstream edge cloud computing framework, which is called OpenStack. It is also used everywhere, for example, in the Amazon, in the Microsoft Azure cloud services. It is the mainstream. In principle, we can make this as big as the data center using the same hardware infrastructure, hardware architecture. Then also we have built different type of the control target. First use case is a mobile robot. We use this open source ROS2 environment, running some navigation application on top of that. Another use case is robot. One is the safety coordination. Because the wireless communication has a very attractive feature for the mobile robot. And in the mobile robot, safety is the most important concern, actually. For example, in some harbor automation, you have a lot of big robots, big AGVs carrying the containers which can be 30 or 50 tons, super big, fully unmanned operation. So if there's any collision in between, there will be a big problem. You have to stop everything and you have to fix the problem manually, a lot of economic loss. And another use case is the teleoperation of the robot. This is also very valuable use case for the robots. For example, remote surgery or telemedicine. You also need this kind of teleoperation. And for both cases, we need to really concern the network performance because they are safety critical, they are time critical. We want to know what's the impact if the network is not perfect. If there's a latency, if there's a packet loss, if there's outage or connectivity, what will happen in the control applications? And then another one is even more time critical, which is the ball and beam. This is a quite popular education kit for the automatic control subject students. And in this system, the controller will know the angle of the beam and also the angle of the position of the ball. It will control the rotating part of the motor to adjust the angle of the beam so that the ball will roll on the beam and reach the target position that you want. And for this process, we require basically 4 millisecond level cycle time. Otherwise, you cannot really close the control loop. And for all these cases, we deploy the applications in the same infrastructure. This was not possible before. If you look at the segments of these use cases, this is robotics, this is another motion control or process control segments. They all often have different software architectures, so different hardware platform. And here we converge them into the same virtualized computing infrastructure. That's definitely one of the values. Imagine in the future, in the factory, if all these technologies are mature enough, you just buy one big server or data center, or you can even outsource this to some third-party service providers. It becomes a control as a service, right? This is another fancy concept. So there is not just the technology motivation, but also the business motivation. So it can create a new business model. If you can use this virtualized infrastructure to support very diverse applications. This is a test bed. And today I mainly introduce what we do with the ball and beam process. On this platform, we first use this layered structure for the server side, for the controller side. We use this virtualization based on the Debian and the KVM virtualization. It's a kernel virtualization machine. And then OpenStack to manage all the computing resources. It can allocate how many CPUs, how much memory you have for each application. Then on top of that, we deploy the soft controller. It is software-based control engine, which can do the cyclic data collection and decision making, then send back the control command. And here we take special tricks in the control model. We call that latency-aware control. We model the process, use the basic, very traditional method, internal model control. But in this model, we consider not only the process itself, we also consider the networks as a part of the process, especially the latency introduced by the network. As I showed, the 5G can introduce 10 millisecond to 50 millisecond latency into the communication. And that process is so fast, it requires 4 millisecond cycle time. So if you just use the wireless network in the same way as you use the Ethernet, you can never close the loop because the latency of the network becomes the major portion of the latency. Then after this, we modeled the network latency and into the control model. Then we managed to do the control, to close the loop. This is the final demonstration after all this tuning. The ball can swap between the two set points, stay there for a few seconds, 10 seconds, then we change to another set point of the ball position. Actually, it is difficult to see the difference by your eyes if you compare the different networks, 5G, Wi-Fi, and Ethernet. No big difference. If we also measured the quantitative accuracy of the control, yeah, you can see slightly some difference. But as I said, if you don't do this latency aware control, if you just use the 5G or Wi-Fi in the same way as the Ethernet, it never close the loop. The ball is always shaking, oscillating on the beam. So this basically suggests the latency aware control is effective strategy for this specific case. Of course, it is not generalized yet, but it is a good indication. There's a good opportunity to really improve. If you remember, the 5G has 50 millisecond one way, then round trip is 100 millisecond. Then you are supposed to do the control with longer cycle time than 100, 200 millisecond. But here you can really do that for this a few millisecond level cycle time. That's a big difference, right? Basically, we can improve the performance by 10 times. And then what is the next? This is just some the current progress. In the future, if we want to generalize, make this really into some serious business, call for automation, what is needed? First, from the technology pushing from this direction, computing and communication topics. First is, of course, the determinism of the communication and computing. We need more real-time, more bounded latency of the networks, and also the software in the server, in the computing. And we also need orchestration. The orchestration is like resource allocation, prioritization, scheduling, all these different tasks, especially when you share the infrastructure with multiple applications. Like 5G, it is supposed to be shared with everyone, right? Even you have the private 5G in factories, it is also supposed to be used by many applications in the factory. It can be the normal IT traffic. It can be the video streams from the cameras. Can also be these real-time control traffics. They have a different pattern of the traffic and also requirement of the performance. So how to do this proper orchestration? And the specific considerations that I would like to emphasize is first, redundancy. This was not very well considered today in the consumer technologies. As I said, in the factories, if you look at the critical factories control systems, so almost everything is doubled or even tripled. Sensors, networks, the cables, switches, controllers, PLCs, and actuators, everything is basically 2 copies running the same algorithm. So if anyone fails, the other one will take over seamlessly. So in principle, we hope the critical control systems will never fully stop working for the whole life cycle. It can be 20 years, can be even, for example, in the energy industry, it can be 50 years. So even during the maintenance, do the maintenance for this setup. Another setup is still running. So that is redundancy and also failover. As I said, if anything fails, it can be the failure of the hardware, can be the failure of the communication, can be some errors in the computing, the software, whatever. You must be able to detect this failure and also take over, activate the redundant hardware or software. Make sure the whole system is still up and running. Then the configuration. Today, the communication and computing stuff in the factory is already too complicated for managing, for configuration. And if we introduce these things, the shared infrastructure, which can support so many different things, it becomes really a nightmare for the operators in the factory. So how can we ease the configuration? Basically, make it easy. The best is make self-configuration. And here, the AI will really play a role. So how should we make the infrastructure learn by itself what is needed? Maybe we just give a very high-level description about the intent. Sometimes it's called intent-based networking or intent-based computing. So that the system, the infrastructure can adapt, can find the optimal configurations, and also dynamically based on the change of the environment, change of the traffic load. Then safety and security. I will come back to this after another column. Then from the control side, as I said, this is more application pooling. I believe this type of effort is even more important and also more urgent, because these applications will really deliver the values of the new generation infrastructure. So without that, without this new cloud 5G stuff, the factories can still work, right? Basically, it has been there for tens of years. Without the 5G, without the cloud. So to really convince the users, the factories, the customers to invest in this new generation, we must deliver new values. And to add some urgent topic, we have shown these benefits. We don't have to wait until the 6G is there. Using the existing 5G, it is mass product, it's available off the shelf, right? We already can do a lot of control. So can we generalize this? We verify, we demonstrated it is effective using the bond beam. But can we do that as a general solution in any other processes? And we need some theoretical work and also experimental work. We also need to expand this to tolerate not just the latency, but also the jitter of the latency. This is a different concept, right? Latency is from here to here, but the jitter means, in average, you will have like 30 millisecond latency, but sometimes you have 10 milliseconds, sometimes you have 100 milliseconds. This is the jitter. Sometimes the jitter is more killing in the control perspective. And also, in the end, we hope we can get some quality of service aware control. Quality of service covers even more aspect, latency, reliability, jitter, and also time synchronization, and some general availability, long-term availability, and so on. And then, as I said, the value creation. So after we have this showcases which can demonstrate the feasibility, so how can we deliver more values of this? And here I just gave a few examples which I believe are valuable from the user's perspective. For example, the hybrid data-driven and the model-based control. And today, the control system is mostly based on the first principles. That's why we call that model-based control. And it is not really benefited by the large amount of sensors, IoT devices, and the data. And also in practice, a lot of processes are not easy to be modeled using the purely first principles. A lot of nonlinear, high-order effects, which cannot be captured very well in this first principle. So then the data-driven methods, some neural networks, some learning, especially the physics-informed learning. So it's not purely data-driven. It should be based on the basic principles so that you can have the bounded performance. You will not make the very stupid mistakes, right? But here, to really get the benefit from the data, from this data-driven approach, we need more computation power. We need a very large storage of the data, and also big enough bandwidth to get the data, to train the model and to run the model. And the second is optimization-based control. Today, for example, the MPC, they are used mainly on the high level of the control loop. Supervisory control, maybe using the optimization to produce the set point of the low-level control loops. Well, actually, one of the reasons is the computation power. It's too complex to be executed in the low level. The low level, as I said, sometimes require a few millisecond cycle time. So the optimization engine takes much longer time. Sometimes it can be second level, right? Depending on how many steps you want to predict. But if we have this super powerful data center, that could change the game. If we can do the optimization with a millisecond level cycle time, that could really make more intelligence into the low level. Because if you go closer to the devices, you can do finer grain control. You can do finer grain optimization. This is basic principles. And then the camera and the sensor. More and more cameras are being used today for the surveillance, right? Monitoring the activities, maybe for security purpose. Can we use the cameras as a generic sensor in the processes? This was not the case before. Actually, one of the reasons is the cameras produce big data, right? Where image is super big, much bigger than the temperature, than the time series data. And also it requires a lot of intelligence to really get the meanings, get the values from the camera images. But if we have this like computation power, if we have enough bandwidth, yeah, we do love to use more cameras in the processes. It's more like the human intelligence introduced into the process. So this is another very attractive, valuable use case. Then augmented operator in the loop. And human workers are already overloaded, to be honest. Even we have a lot of robots, we have a lot of DCS software that are supporting the operators to operate the factories. But the operators are still overloaded because more and more complexity of the whole system is introduced. Before, one operator just need to take care of one machine. Today, you need to supervise the whole process. And also during the most recent pandemic years, this becomes really the challenge. So how can we operate the factory, the production facility with less human intervention, with less human effort, especially for the decision-making part. And this is really valuable thing. Then the event-triggered control. This is now another aspect. From the control perspective, it is not urgently needed, but it is very much meaningful after we have this cloud phone infrastructure. In the past, the networks, the controllers are customized for the process. And even you have some room, unused capacity of the network and the computer, it's just there. Nobody else can use it. It's wasted, of course, but you don't have the way to utilize it. But today, after we have this virtualization, after we have the infrastructure shared by multiple users, multiple applications, it becomes possible if we can save some traffic, save some bandwidth from communication and computing. So these saved resources, saved bandwidth is valuable for all the users. It can be used by more applications, or it can provide a better experience for the other applications if they are less critical. That's control tasks. So that becomes relevant. If we use the event-triggered communication and computing and control, of course, we can save a lot of resources. So those bandwidths can be used by many other applications. This will really reduce the overall cost for the factory owners. This can help the adoption of this new infrastructure. Of course, we need to have the other use cases first. This can be the secondary urgent level. And then the functional safety and security again. So I like to emphasize this on the top, actually. Security and safety, they are not solely in the communication, computing, or control. It is really system level challenge. And for example, for the communication part, when we say functional safety, from the communication perspective, it's about deliver a message, especially some alarming message, maybe emergency stop message over the network. We need to guarantee first, this message should be delivered before the deadline. The deadline is calculated, derived based on the safety process. For example, if you want to stop a mobile robot, so from you sending the message until the robot is really stopped, there is some time, breaking time. It is not zero. So when we make the machine, when we make the robot, we calculate this time, we can estimate this time. Then your communication and computing, the whole process, need to guarantee you must deliver this message before this deadline. So this is really required by the safety regulation. And the second is, you must make sure there's no error bit, a single bit error in this message. So this requirement is very critical. Sometimes it requires 10 to the power minus 13, minus 14 level bit error rate. So you should tell me, basically, if there's any error in this message, you should notify me there's an error. Maybe you cannot correct it, but basically you should detect it. So you should provide a very strong error detection coding in the message. But this is the practice today. And sometimes it's called black channel approach. So that means the safety communication layer doesn't care what is the networks. We assume the network is not trusted. It has packet loss, it has error bits in the message. We just take care of that ourselves from the top level. But this introduces a lot of overhead and also makes this even not possible today to meet all those requirements, even we have improved the wireless very much. Then here I propose to have some gray channel approach. Gray channel means we need to really know the channel. And from the control perspective, we know this channel is different from another channel. This one is 6G, is Wi-Fi 7, it's not Ethernet. So let's keep this in mind when we do the control logic. This is from the control side. And so from the communication side, if, for example, if the 6G network knows that, this packet is for safety message, let's skip over all the other overhead. Let's apply the very strong error detection coding in this message. And also we support that using a dedicated physical layer parameters. You don't have to develop a totally new physical layer, but you give this special care of this safety message and transmit that with the minimal overhead. And you do the automatic retransmission, automatic or stronger error correction, and so on in the physical layer, in the low layer of the wireless communication. This, I believe, will largely improve the performance, but it is not there yet. Then another aspect about cybersecurity. Before, it was also like some black box approach. The cybersecurity managers or engineers in the factories, they have a very long list of the security policies. For example, you are not allowed to use cloud in this process. You are not allowed to use wireless communication. You are not allowed to use a single factor authentication, for example. These are their policies. So they follow the policies. They do the assessment of the security, and they do a lot of encryption, decryption using the password. But for me, that's not enough. We need to know the process. For example, imagine if the attacker has cracked all those encryption, decryption mechanisms. For example, using some social engineering, you lose your password. This was really the root cause of the most famous accident, security accident happening in the recent years. So the VPN password was stolen by someone, by some phishing email, or just by some face-to-face contact to the persons, and they got the password. Then all your security mechanisms becomes useless, right? They really invade to the critical control system, and then they send some fake command, damage your system. And here, the gray box approach is exactly addressing that kind of issue. If we know, for example, this machine, the temperature cannot be higher than 100 degrees. If you send a set point which is higher than 100 degrees, it should be like stopped. And also you will trigger a security alarm. This is simple from the control perspective, right? So if the control engineers, if the physical knowledge, if the process knowledge is engaged in the development of the security process, security solution, this can really solve the problem. This is what I call the gray box approach. So both of them, you can see, we need the knowledge from the both sides. It's definitely cross-disciplinary research. And that's also my personal preference. So in the company, as Kale said, we have the vertical coverage of the subjects. As one person, I was like, I forced myself to learn the things from all these subjects, because sometimes, of course, when you formulate a project team, you can have the person from control, from communication, from security, from software engineering. But I think to really have some synergy of the knowledge, especially for these disruptive ideas, you need to have something really crossing the disciplinaries in your brain. So I do love to learn these broad subjects and also put the knowledge together. Yeah. Yes, this is the last slide I managed.
Okay, thank you.